Everyone. In this video, I'll be talking about the IMLS database. IMLS stands for Inter-Modular Linker Database. And this is a database that focuses on all the sequences or the segment of DNA that are present between two successive modules. Modules within a non-ribosomal peptide biosynthetic gene clusters. So that's exactly. So we'll be extracting all the linkers that are present between these modules within their biosynthetic gene clusters. So let's just go ahead and click on the IML database. We'll see a drop-down menu of two sub-items. The first one is the MIBIC database, or the MIBIC intermodular linkers. And by MIBIC here, it stands for actually the minimum information for biosynthetic gene clusters. This is a collaborative collective work of several research institutes that created a repository of all so far well annotated and identified biosynthetic gene clusters that produce natural products. And since the natural product spectrum is pretty big, my tool is just focusing on a specific type of natural product, which is the non-ribosomal peptide. And so I took the subset of I took the subset of NRPs from the MIBIC database, and I applied my parser, the one that we talked about in the previous videos. I applied my parser onto those non-ribosomal peptide clusters, and I extracted all linkers, all intermodular linkers within these clusters. So let's just go ahead and see how does it look like. So first of all, the result will come in a tabular format, in table form. So you will see that totally I have from the MIBIC database, I was able to extract 585 linker, and this is how the data is actually presented. So first of all, you start by A1 and linker and A2. What do I mean by A1? Literally, the linker, it links between, it's a physical segment of DNA that links two modules. And the A1, it literally refers to the amino acid or to the substrate that is activated by the first module, while A2 it represents the amino acid or the substrate that being activated by the second module. And the linker is literally the segment of the segment of amino acid sequences linking these two modules together. So this is how I will be presenting the results, and this is just tell you the length of my linker, and this linker was extracted from which cluster, since the MIBIC ID, every cluster within the database or within this repository, they had a MIBIC ID, and it also tells you what this cluster is producing. For instance, this cluster is responsible for producing the penicillin, while this one is producing the cyclosporine, and so on. And it tells you from which organism it's actually producing the results. So this is pretty much it, and every table is sortable. You can actually sort it because of by length. You can sort it. You can also do multiple sorts by amino acid, by product, and so on and so forth. And the coolest feature as well is you can actually search, and it goes pretty fast. So you can actually filter by every column. So you want the A1. If you want, for instance, all the pairs that alanine, all the linkers that link alanine to serine. And for instance, there is no alanine serine in this case, but you can do like alanine ASPs. For instance, here we go. You got these, and it tells you the information. Every time you filter, it tells you exactly how much is it. For instance, we have 47 entries where alanine is at the A1, and regardless what is coming the A2. And you can reduce this by, if you have one alanine, then it was reduced to 18. And of course, there's the pagination that you can go and scroll from the first to the last. And here you get to control as well how many entries do you want to see, how many results. I think 10 is a good default, but you can increase it as much as you want. You can see you can have 10, 20, and 25, 50, and 100. And another feature also is you get to export the table, the result that you want as a CSV file. And here we go, it was saved, and you get actually to open it and then have it on your local machine. So this is as far as the Mavic database. Now let's talk about the NCBI bacteria. So the second database, it is actually a much bigger database. It is literally based on all the bacterial genomes that being so far sequenced and submitted to the NCBI database. So we're talking here roughly around 68,000 bacterial genomes has been scanned for and searched, or has been scanned for non-ribosomal peptide clusters, and all the cluster that has been collected after scanning these bacterial genomes. We ran our parser on all those identified clusters, and we extracted all intermodular linkers from all the newly identified clusters. And we extract all these linkers and we put them into this database. As I said, this is a much bigger database. Usually when you click on it, it will tell you to wait. Since exactly this is the message that will show up. It says it's a much larger database, so please give it up to a minute or two, depending on your internet speed. So I think, as it says, based on your internet speed, it might go maximum a minute. Others might take 2 to 3 minutes. You get actually to see the progress of the download or the downloading of the page, either through this bar based on your browser that you're using. So in Safari, you get to see it here. I think in Firefox as well. In Chrome, you will see down there exactly on this corner, sort of uploading the page. It's a percentage bar, so you will be able to know when it's actually done. But as I said, it takes between 2 to 3 minutes maximum with lower internet speeds. And since I didn't want to wait for you guys to do this, so I have already opened it in a different tab, and just to accelerate the process. So this is the NCBRFC. Once again, we scanned 68,000 bacterial genomes, and we identified all non-ribosomal peptide clusters, and then we applied our parser to extract all intermodular linkers within these clusters. And it's exactly the same thing as in the Mavic database. Every linker is represented by the first amino acid, which represents the substrate that being activated by the first module, and the substrate that being activated by the successive module, and the linker between them, which is the segment of amino acids, the length, the organism that this cluster was identified from, and hence the linker was taken from. And here, this is if someone wants to reproduce the same result and want to know exactly what is the genome and which strain did we work with, this is exactly the file to the FTP path to the genome that we actually use to collect the cluster as well as the linkers. And you can see this is a much larger database. As I said, the other one contained 500. This one is 17,445 entries. Yes, it might take two to 3 minutes to download, but once it's downloaded, the search engine is really fast. So let's say alanine, let's say porcine. Here we go. You have now 29 entries across several species and organisms. You get also to, if you want to have all the 15s, and you have, this is the search for all the linkers that have the length of 15, and you get as well to, and the same thing, you get as well to show 10, 15, 25, how much you want to see, how many rows, how many results, and you get as well to export it as a CSV file on your local machine. So this is the main databases based on the pipeline that we built. That's it. That's exactly what I want to say about the IML databases. And later on, in the third video, when you go to the NRPS design, you will see how can we actually use this database to produce novel NRPs. So this is where The whole process starts by getting the cluster, parsing the cluster, collecting the linkers, putting the linkers into the database, and then designing novel peptides by using the database that we actually created that will lead them to novel NLP design. That's the whole concept of my project. Thanks so much.